Hello everyone. Now in this video, uh, in today's lecture, we are going to discuss about the remaining topics of standard and extended form games. So firstly, we will be revisiting the Pareto optimality that of course we have already seen as part of theory, and we will see what is the characteristic features of the Pareto optimal or efficient principle. Okay, and then we will talk about the games in extended form, and then the solution concepts for the games in extended form. So before we go further, let's first see what we have seen in our previous class. So till our previous class, we tried to understand what is game theory, what are the different principles and solution concepts of game theory, how we can create a payoff matrix, how the what are the different standard forms of games, and we saw as part of solution concepts the different solutions like max min strategy, social welfare strategy, dominant strategy, iterated dominant strategy. Then we went forward and understood about Pareto optimality and then the Nash equilibrium. A few of the solution strategies we discussed, and we found how given a particular problem or how you can create a payoff matrix, and if the payoff matrix is given, then how you can create the different how you can find the solutions to the different strategies. Okay, now before understanding Pareto optimality on a more wider aspects, let's first try to revisit what we studied in our Pareto optimality principle. Okay, so we understood that in case of Pareto strategy or Pareto optimality, so we understood this concept that whenever a strategy, let us suppose S is given to you, so in that case, here is the Pareto optimal principle. Okay, so here specifies the Pareto optimal principle. It is also known as Pareto efficient strategy. Okay, so both the terms are used interchangeably. Okay, so what it suggests is if a strategy S is given, so that strategy S is considered to be a Pareto optimal if let us suppose there is no strategy S dash in such a way that when you move from S to S dash, then the one of the agents will gain and other of the agents gets worse. So the concept is very simple, that is represented with the use of this uh, formal definition in your mathematical form. Okay, and we have also seen that there is a very simple limitation that it is unstable at certain times because of the converging of the system. Okay, so we will see at length what basically is Pareto optimality. Okay, by let's see by first talking about certain points. Okay, so now before saying कि भाई Pareto optimal है कि नहीं कोई solution, what are the different points, let's see. So the first point says okay, the first point says that given an initial situation, okay, a situation, initial situation, some situation is given it to you. Okay, so there is a concept called Pareto improvement. So what it is? So basically Pareto improvement is a new situation that is different than the initial situation. Okay, where some agents, where means in the new situation, some agents will gain and no agents will lose. Are you understanding? So I'm saying that The important point over here in this point is what we are trying to focus is Pareto improvement. Okay, so what it says that you can say that given an initial situation, you have a situation given to you. Now that particular situation is known to be a Pareto improvement situation, or a new situation if you are trying to find out. So that will be a Pareto improvement over the initial situation when there are some agents, they will gain what? Utility. In terms of utility we are talking about, है ना? And no agents will lose. Okay, so that is the case. It's not like if somebody is gaining and not thinking about the other agents. So of course somebody can gain, but it doesn't mean that others may lose their utility. Okay, so this is one point. What second point says in terms of Pareto optimality, that you may call a situation to be Pareto dominated, or when it has Pareto improvement. So what does it mean? Ki, okay, fine. Now you found a Pareto improved situation, correct? Now that particular situation can be known as a Pareto dominated situation if it has Pareto improvement. Okay, so here the point that needs to be underlined is Pareto dominated. Okay, and now we are moving towards our third point. It says that a situation can be known as a situation is called Pareto optimal or efficient. I told you before also, it is known as Pareto efficient or Pareto optimal if no change could lead to improved satisfaction of all the parties, of all the parties means all the agents involved, and doing the work on the basis of which they are getting the rewards. Okay, now what this particular point says that now we have already discussed what is Pareto improvement, what is Pareto dominant. Now a particular situation can be called as Pareto optimal or efficient if there is no change that could lead to improved satisfaction of all the parties. Okay, means all the parties, if there is no improvement, means a situation is given from where you cannot improve further. And improve further means if it is if two agents are involved, means both the agents should improve further. Okay, so if there is no improvement for both, then it is called a Pareto optimal situation. Okay, so let us take an example. Let's say that you have an outcome O, okay, and you have an outcome O dash. Fine. So now if we say that outcome O is better for every agent, this is better for every agent. Outcome, if you move from outcome O to O dash, and it is better for every agent. Okay, now when we say that outcome O is better for every agent, in this case what we can say? So point number one. So point number one says that any agent or an agent will definitely prefers O, okay, over O dash strictly. Why? Because it is better for each and every agent, correct? And what do you mean when we say O is better than O dash? So when we say that O is better than O dash, O is better than O dash, it implies that O Pareto dominates O dash. We discussed it in last this now that a situation is called Pareto dominated if it has Pareto improvement, and we know that there is an improvement and O is better than O dash. What do we mean when we say O is better than O dash? Means O basically Pareto dominates O dash. Okay. Also, we can say that any outcome O star, let us suppose, okay, is Pareto optimal or efficient. You may call either of both. Okay, if there is no other outcome that Pareto dominates it. Fine. So with this, the concept of Pareto optimality, this is one of the examples. Now uh, we have seen this example now, like what are the different games. Okay, so let's revisit those games and try to find the solution. So let us take the first game. What was the first game? So it was the game of prisoner's dilemma. Okay, so let's talk about prisoner's dilemma. So in prisoner's dilemma, what we last time what we tried to make the payoff matrix in our last class. So let's do the same over here also. So there are two prisoners, okay, and we have a 2 by 2 payoff matrix where either they are cooperating for C and defecting for D, cooperating for C, defecting for D, okay, and there are two players A and B. Fine. So when we say prisoner's dilemma, our uh, values or utility values were 3305, 50 and 11. Okay. Now if I want to find the Pareto optimality, how to do so? Okay. So the concept is very simple. What it says that if from some situation, what is this particular situation? So here situation is also known as strategy. Okay, so from a strategy S, let us suppose this is our strategy S. So if I move from this strategy to next strategy, let us suppose from 3 to 3, I would like to move to 0 to 5. So in that case, if somebody is getting, let us somebody is gaining something, so it doesn't mean that the other agent should lose. So if that is the condition, in that case, you can say that that particular strategy is Pareto optimal. Okay, so let us first talk about your DD. Okay, when your player A or prisoner A tries to defect, so the utility is 1, and prisoner B tries to defect. In that case, utility is 1. So let's see how it happens. Okay, so now we can say if I want to move from 1 comma 1 to 0 comma 5, definitely one is uh, uh, one is this one, your first one, that is for B's one, it is not gaining something. Okay, and otherwise if we say A is 1, so in that case this one is gaining something, but at the same time it is losing. Okay, so this is not a good situation. Okay, so you can, if it is losing, then we should not go for such kind of scenario. Similarly here, if we move from 1 1 to left 5 0, here also one agent is gaining but another is losing. The situation is that one agent must gain, but not at the cost of another agent losing its utility. Okay, similarly we can say from 1 1 to 3 3. So definitely from 1 1 to 3 3 the concept is both of them are gaining something. Okay, so now the first, it cannot move from 1 1 to 0 5 1 1 to 5 0, and it can definitely move from 1 1 to 3 3. So देखो इसको ऐसे समझो कि a problem can be reduced. So if it is in the reduced form, then it is Pareto optimal. Okay. If it is going to be reduced, or if it is going to be in the next step, so there is an improvement, correct? So here from 1 1 to 3 3, basically there is an improvement that is done. Okay. So that's why we can say that our 1 1 cannot be your, it cannot be a Pareto optimal state, because it is two situations are there where one is gaining but other is losing, and one situation from 1 1 to 3 3 is there where both are gaining but they are getting improved. Okay, they are not optimal. Okay, so let's see another strategy. If we move from 3 3 to 0 5, you can see that from 3 3 to 5, one is gaining and another is losing. 3 3 to 5 0, same situation. From 0 5 to 3 3, same situation. 0 5 to 0 5 and 0 5 to 1 1, the situation is same. Okay, so we can say that these three, this one, this, I'm sorry, so these three, like 3 3 0 5, okay, and 5 0, they all are Pareto optimal. So we can write our Pareto optimality as CC, CD, and DC. This is our Pareto optimal state. Okay, now let's talk about another situation. So next problem was the problem of battle of sexes. Okay, so let's see that in battle of sexes we saw that one wants to go and play ice hockey, second wants to play football, but they both want to do the same activity together. Okay, so that's what the battle of sexes was. So let's see it, what happens. So the we had 2 by 2 payoff matrix where I stands for ice hockey and F stands for football. We are two players A and B, or Alice and Bob. Okay, now let's talk about the Pareto efficiency. Over here the utilities are 4 7 0 0, okay, 3 3 and 7 4. Now let's talk about the Pareto efficiency. Now what is happening over here, if we see, let us talk about when we move from 3 3 to 0 0. You can see that if you move from 3 3 to 0 0, one both the agents are losing, so definitely it cannot be Pareto efficient. Okay, similarly if we are moving from 0 0 to 3 3, both are gaining. So both are gaining means there is an improvement, but optimality, that we cannot say. So since similarly there is an improvement for all the situations. Okay, now if we talk about your II, that is 4 comma 7, you can say that, see over here, that from both the situations they are getting improved from 0 0 to 4 7, or 0 0 or 3 3 to 4 7, or they are improved, you can improve from 0 0 or 3 3 to 7 4. Okay, similarly if you try to go from state 4 7 to 7 4, you can see that 4 is gaining. Okay, because 4 is getting increased to 7, the utility 4, and similarly 7 is losing. So definitely you cannot go, because one is gaining and one is losing. One is gaining doesn't mean that one should lose. Similarly 7 is losing its utility but 4 is gaining, so you cannot. So in this way we can say that you have two states, okay, which are those two states or strategies II and FF, which are Pareto optimal. Okay, so similarly, let's talk about the game of chickens. If you remember, in the last class we talked about and we discussed at length and saw the problem of game of chickens, in which two maladjusted adult boys, they were trying to drive their cars towards each other, okay, and trying to crash. So one who was swerving and trying to means if they both will not swerve, then in that case they will crash, but they will get more points, okay. But if they will swerve, then accordingly we were having the points, okay. So what were those points? Let's have that payoff matrix, okay. So it was again a 2 by 2 payoff matrix where C was for crash, S for swerve, okay. And what was our utility? What were the utility values? 1 5 and 1 1, okay. Now let's see over here how optimality, whether it works over here, how it works and all, okay. So concept is very simple. Now again you have to see that how from where to where it is going and how. So if you see from CC, so from -1 you are improving to CS, you are improving. If you go to downwards, you are improving over here, you are improving over here. Similarly, if you say over here 1 1, so from 1 1, if you go to -1, you are losing. So from if you go from 1 to 5, okay, upwards if you want to go, then from 1 to 5 you are gaining, but at the cost of S, that is your swerving, that is not doing anything. So that's why you cannot move. Similar situation from 1 1 to 1 5, okay. So you can say that your CC and SS cannot be part of your optimal Pareto optimal solution, okay. Now if you see over here 1 5 and 5 1, so definitely since these are get from CC, if you go downwards to 1 5, it is an improvement. From CC if you go to CS, it is an improvement. Similarly from 1 1, both ways it is an improvement, okay. So let's talk about from 1 5 to 5 1. You can see over here 1 is gaining utility and going to 5, and 5 is losing its utility, and vice versa from 5 1 to 1 5 also. So over here you can say that 1 5 and 5 1, they both are Pareto optimal solution, okay. So here CS and SC are your Pareto optimal solution, fine. So with this, what we came to know that your Pareto optimal solutions can be found on the basis of three important things. First, that I told you at the start of the class. First, that a new situation is found, that is your Pareto improvement. Okay. Then second, is there any Pareto dominated? Okay. And thirdly, on the basis of Pareto improvement, if one is gaining and another is not losing, then it is a Pareto optimal solution. Okay. So based on that, if we talk about our uh, the concept of Nash equilibrium that we already discussed. Okay, so what we discussed, whatever the solutions we have seen, all these solutions make it clear that it is not a simple matter to define what is the best answer, because you are getting two strategies, sometimes you are getting four strategies, sometimes you are getting no strategies, okay. So it is somewhat difficult, and it is not very simple to define what is the best answer. However, this we show with 2 by 2 matrix. No? So the complexity increases if we increase the number of rows and columns. Okay, means the number of possibilities if we increase, and this we are seeing for two agents, correct? Now, if we increase the number of agents also, it matters. So when the number of players are multiple, there are multiple players. So what is best? So what is the best? It only depends on how much we are willing to respect the agent's selfishness. Okay, its rationality, and there must be a trade-off. Okay, between the utilities, so that the optimally fair solution can be achieved. Fine. Now, most common problem that we face when designing multi-agent systems is the existence of multiple equilibria. We have seen in the case of Nash equilibrium that multiple equilibria exists. Okay, so in that case, it becomes somewhat difficult to design the multi-agent systems. And so, extra coordination mechanism must be ensured in such kind of scenario so that the different agents come to the same strategy or converge to the same strategy. Okay, so this is and that's what you have seen in your Pareto optimal solution for prisoner's dilemma. If you remember that your Nash equilibrium was 1 1. So what Nash equilibrium states that the equilibrium for this particular problem is 1 1. Okay. So the solution, if 1 1 is achieved, so it means that if both can defect, they get less number of sentences at the same time. They both are getting together something that is benefited for both of them, both the prisoners. So that's why 1 1 is the best solution for Nash equilibrium. However, if you see that prisoners in prisoners dilemma, the Pareto solutions are all three except 1 1. Okay, so this also proves our statement where we discussed that the Pareto optimal solutions cannot be a strategy that is Pareto optimal cannot be Nash equilibrium and vice versa. Okay, but your social welfare solution can is always a Pareto optimal. You can see the social welfare solution. What is the solution? So 3 plus 3 is 6, 0 plus 5 is 5, 5 plus 0 is 5, 1 plus 1 is 2. What is the maximum of all? 3 plus 3 equal to 6. So your social welfare solution is CC, and you can see that your optimal solution is also CC. So a social welfare solution must be a Pareto optimal solution. That you must remember. So this is this becomes a very important thing when we talk about the uh, uh, problems and their solutions and different solution concepts. Now you see, in case of prisoner's dilemma, one another point must be noted that dominant strategy was to defect. If you remember that the dominant strategy, if you remember, in case of prisoner's dilemma, it was that A should also defect and B should also defect. है ना? But what happens if they are the dominant strategy is defect means they are getting a utility of 1 comma 1 है ना? But there is a question that may come into your mind that if both players could have received higher utility by cooperating, you can see 3 comma 3. So if they cooperate, they will get more utility. Here I'm not say when you are representing your problem in terms of utility, so it is a number, na? So you are getting more utility when you are cooperating, but you are getting lesser sentence when you are defecting. Okay, so that's why it's called the problem of prisoner's dilemma. Okay, that all the solutions are giving you different answers. Okay, what all the strategies, Nash, Pareto, dominant, social welfare, they are giving different answers. Okay, so if you think logically, that's what I'm talking about. So if they cooperate, they will get both of them receives higher utility, and there is no comparison because they are both getting higher utility. So even since they are playing this game simultaneously, so even though they do not see each other, they are getting the utility that is benefiting for both of them, correct? So this is a problem exactly where they should have cooperated, but they defected and they went out of this game with less number of lesser sentence. However, if we talk about getting more utility, okay, so there are different solutions, है ना? So one solution could be that you just ask the two prisoners to play that particular game repeated number of times or more number of times. Okay, so with this concept, a new topic that we will discuss is repeated games. So what we were playing as of now, they were not repeated games, correct? They were playing and they were getting the values. Okay, now what it says, your repeated games, so it says that uh, uh, just let those two players, okay, let two players to play the same game multiple times or multiple number of times. Fine. So what will happen? So this if it's a prisoner's dilemma, so if it is going for repeated number of times the prisoners are playing, then in that case it will be known as iterated prisoner's dilemma. Fine, iterated prisoner's dilemma. So what is happening over here? So we can say that so repeated games with a finite horizon are special case of extended form games. We will see what are the extended form games. We will see in coming just a few minutes. We will see what are the extended form games. So this is what the concept of repeated games is. So the repeated games may have a finite horizon and may have an infinite horizon. So if a repeated game has a finite horizon, what does it mean? By you are repeating the game a multiple number of times, that is fine. You are playing the game multiple number of times, but that multiple instances must be finite in nature. Na? So why it's called horizon? So horizon is the place where sun and earth meets, appears to meet. Okay. So that horizon, if it is finite, means your solution can be obtained in finite number of finite times of multiple playing, or finite number of times of playing. Then this is known as a special case of extended form games. Okay, then it will be known as the special case of extended form games. Fine. Now it is what you are trying to say by this. So we will say that, let us suppose repeated games for prisoner's dilemma is there. So it will be known as iterated prisoner's dilemma. So we will ask the prisoners to give the answer to the questions of the policeman 50 number of times, let us suppose. Okay, so what will happen? So there are certain conditions that we must understand. Okay, so let us suppose uh, we have two prisoners, okay, A and B. So what will happen if A knows that he last round he can defect, because defection means less number of means less amount of prison sentence, correct? So what it will do? So he knows that the your defection is the dominant strategy. So what will be done? Like we will play for 49 number of times, and finally in our 50th time what we will do, we will defect. Okay, so if a player has realized this particular situation, correct, where he can play 49 number of times nice to the other player, and then 50th time it will defect. Okay, and also it may be the possibility that the other player has also realized the same, कि भाई I will also play for 49 number of times and I will also defect at the second round. So what will happen here? There is nothing to gain by cooperating at 49th step, correct? So you will, what the other player will do, he will defect at 49, not he will not wait for 50th step. Okay, so what was happening, let me explain it once again. So both of them both of them have 50 rounds to play. So 49 rounds they may be nice to each other, and 50th round they may think that okay, let's defect. Okay, so one player if thinks like that, the second player may be having this in mind, okay, this player is going to defect in the 50th round, may be possible. So if I will choose the same, try to cooperate, so that will not result in a good solution. So let's better do one thing. I will defect in the 49th round only. I will not wait for the 50th round. So now think that if player B has had this in mind, that I will defect in the 49th round. Maybe possible the player A will defect in the 48th round, then 47th round, then 46th round. So they are playing, है ना? They are coming backwards. Okay, so this backward induction can be repeated any number of times. Okay, so it can be repeated in such a way that we can come up to the conclusion. And since we cannot ask them to play infinite number of times, nah. So finite number of times, and a rational strategy, what is going to be is always defect, है ना? So what is happening over here? Rational strategy also you are getting as defect. Also the backward induction, if you are following, so if A is trying to defect on 50, then B will think to defect on 49, then A again will think of defect at 48, so it is going backwards. Okay, so this is the way that must be, and this is the way we think it must be, but people don't act like this, na. It's not like कि भाई every time you think rationally, one of the situations, है ना? So what could be the solution? So cooperative equilibrium could be one of the situation. Okay, so what happens over here? So we will not fix the known number of interactions, है ना? What we will do is, instead of fixing the known number of interactions or finite number of times you are playing the game, let's talk about probability. Okay, so what will be the probability? So there may be a chance that every interaction will be the last interaction. Okay. Now I am not telling the prisoners are not knowing that 50 number of rounds or 50 number of chances will be given to me. Instead, the prisoners may think that this chance may be my last chance. And since we are talking about chance, so that's why the probability comes into a picture, that there is a small probability that every interaction will be the last interaction. है ना? So in that case, what will happen? The players may never know कि which one is the last interaction, is the present one or the next one or the one that is going to play. Okay, so what will happen in this scenario? In this scenario, the dominant strategy can be converted to cooperate with a certain probability. Up till now, the defection was done because they know that, okay, I have this many chances left. But if the chances are not known to them, and they know that there is a small probability that the current iteration is the last chance for me, so in that case, somewhere the dominant strategy is to convert this defection to cooperate. Okay, so see why this problem is getting, we are discussing this problem to a very big potential, and it has a very big potential, and why we are discussing this topic at depth. This is because of very simple reason that this problem was utilized at different levels, implemented, and they tried to find the solutions out of it. And if you go for crime psychology, there in psychology they use such kind of techniques. Okay, so probabilistic technique. Okay, and this is very random in nature. Okay, so we will not go into those randomness around, because otherwise we will go into the statistics, but we must understand what is the case. Okay, so herein the concept of folk theorem we must know. Okay, then we will talk about how the solution concepts for the repeated form of games was formalized. Okay, so the concept of folk theorem, let's talk about that. So what basically is folk theorem? Okay, so folk theorem says that if you have a repeated game, okay, let me write it for you. So in a repeated game, any strategy which is not Pareto dominated. Now you know na what is the meaning of Pareto dominated. By another, not Pareto dominated means it is not, there is no improvement, है ना? from one strategy to another, and where every agent gets a utility that is higher than its maximum utility. Maxmin means the utility that is found with the use of Maxmin strategy that we have already discussed. So it will be a feasible equilibrium strategy. See, coming to equilibrium is very important, है ना? Because the equilibrium strategy will tell you that what could be the best solution out of it, or what is the strategy on which you can actually trust or rely on, so that both the agents do not get uh, means get some improvement, or they get some rewards in such a way that both of them are winning, or if they are losing, then they are not losing in so much so bad way that they are not comparable at the end. Okay, they must be comparable, na? Both agents are selfish, they are rational, they should try to maximize their utilities. So what it says, this folk theorem, that if you have a repeated game, then any strategy that is not Pareto dominated by another. Okay, so that strategy is not Pareto dominated by another means if you have S1 and S2, they are these are two are strategies, and these two are strategies of a repeated game. So S1 is not Pareto dominated by other means there is no improvement from S1 to S2. Okay, so and every agent gets a utility that is higher than its maximum utility. Okay, so every agent, let us suppose the agents are A and B, both the agents, they are trying to they are getting a utility that are higher than their maximum, individual maximum utility, and when they play the game, the maximum utility with the use of maximum strategy, of course, है ना? So then if that is the situation, then that particular strategy S1 is known as feasible equilibrium strategy. Okay, so this is what the concept of folk theorem is. Now what happened, so I told you, na, like uh, what is happening over here, the agents are agreeing to a strategy that gives everyone at least max min and is not Pareto dominated, है ना? So what is happening over here, that we are trying with the use of this particular concept, uh, 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 a person called scientist called Robert Axelrod. Okay, Robert Axelrod. Okay, in 1980s, what he tried to do, he tried to give this particular problem of iterated prisoner's dilemma. Okay, he gave to submit the different Fortran programs to his students. Okay, and what they were supposed to do, they were supposed to play this particular iterated prisoner's dilemma game for 200 rounds. Okay, so who was the winner? The winner was the person who has accumulated most points, है ना? So in that case, what they do, what are the different strategies they took? So there were different strategies, like one was all D. So all D says that all of the players defect. Okay. Second strategy was random. Okay, so random means they must pick an action randomly. Cooperate, defect, cooperate, defect. Okay, they must, all the agents must pick that particular thing. Third is tit for tat. And what was the tit for tat strategy? So first you have to cooperate in first round, and then whatever the other player is doing, last time you do that. For instance, if A played cooperate and B played, and let us suppose, so A played first time cooperated and B defected. Okay, so the next round, this is your round one. So in the next round, tit for tat, A will definitely uh, defect, so that is That was the strategy. Okay. Then your fourth strategy was the tester. So what tester strategy is doing? So it used to defect on the first round, and if other players defects, then play tit for tat. What does it mean? So if A defects in the first round, and if B also defects in the first round, then A will again defect, है ना? Because they are playing the tit for tat, है ना? So it will defect. Similarly, what was the situation in tester? If A cooperates, okay, and then cooperate for 2 rounds, then defect, है ना? Means if A is cooperating, then it has to cooperate for 2 other rounds. This is round 1, round 2, round 3, and then it will defect. Okay, so this was one of the strategy. And fifth one was called jaw strategy. What was the jaw strategy? Play tit for tat, but 10% of the time they have to defect instead of cooperating. In this, they have to play tit for tat only. Okay, but 10% of the time they have to actually defect instead of cooperating. Okay, so these all 5 different strategies they played, and it was found that this, this winner was the tit for tat. Finally, the more number of points were accumulated using the tit for tat strategy. Okay, so actually, this was one of the situations in which you can implement using such kind of strategies. You may have some other mechanism, and you may think of that mechanism and try to find out which of those mechanisms works best. Okay, so this, I told you that it's already this is a very good problem that is discussed in the case of crime psychology. Okay, and if you are interested, if you somehow join CBI or such kind of agencies, okay, so therein in your training and all, you will be taught such kind of psychologies. Okay, now one way of analyzing the repeated game I told you na. Another way is, so what is this way of analyzing repeated games? By probability ka use karo. So another way could be that you go for some learning algorithm, है ना? Learning algorithm. What this learning algorithm does, it tries to determine which strategy their learning will converge to, है ना? भाई इस लर्निंग एल्गोरिथम से क्या पता चलेगा कि first let us suppose there are two players A and B. तो player 1 says okay, I will cooperate. Then they have to learn based on their past results and current strategy, and on the basis of what the other player is doing. Okay, so if it is not known ki bhai what the other player is doing, sometimes it happens that the policeman comes and policeman gives some idea ki you are not defecting, that person has defected, or you are not cooperating, that person has cooperated, and they are getting this many number. He is going to get free, or he is not going to get something like that. So that kind of situation. So based on the situation, they must learn, and they must think that which strategy to choose, which strategy to choose that will converge my solution, that will converge, so that I will get maximum benefit. My rationality will be higher than the rationality of the other prisoner. Okay, so this we will see in our next unit, we will see how learning algorithms can be applied. Now let's talk about games in extended form. So what we were discussing till now was games in normal form. We discussed at the start of game theory that there are 2 forms of non-cooperative games. One can be represented with normal form, and second can be represented with extended form. When we represent our problem in normal form, in that case, a payoff matrix is used, and it was given by the person called, that particular concept was given by the person called Shapley, the researcher scientist who gave this particular thing. है ना? Now let's talk what is the game in extended form, है ना? So we will see it one by one with points to understand, है ना? अभी क्या हो रहा था? The players were playing the game what simultaneously. Now in here the players play games sequentially, है ना? So players take sequential actions. First point for your games in extended form. Fine. Now, second important point, games in extended form are represented using tree data structure. Okay, using trees. Okay, now definitely if tree is there, then there must be branches and leaf. So if there what are the branches? So branches at each level are players actions. Fine. And if we talk about the leaf, what is a leaf? So it will be the payoffs. What is a payoff? So in your payoff matrix, when you are getting utility, है ना, जो मिलता है ना 3, 3, 2, 1 for both the players, you are getting utility. So they are also known as payoff. Okay. So at leaf, the payoffs are mentioned. Fine. Then we have third important characteristic of games in extended form as it represent simultaneous actions. Also, now how you can represent that? For that you use the dotted ellipses. Okay, so with that you represent your simultaneous actions also, but basically players take sequential action. Okay, now if we say what is a dotted ellipse, है ना, why we represent with the dotted ellipse? If you find that there is a dotted ellipse in the games in extended form, the tree representation, so what is that? So basically dotted ellipse, it grouped together. Okay, it groups together the nodes. And what are those nodes? Okay, so the nodes are equivalent to rest of the agents. Fine. So this is what the concept of dotted ellipses. Now, again one question comes into the picture, what is equivalence? है ना भाई, मैंने तो बताया equivalent to rest of the agents. There are certain nodes which are equivalent to the rest of the agents. So if those nodes are there, then we will form a dotted ellipse. And if dotted ellipses are formed, it means that the simultaneous actions are taking place. Okay, but what is the equivalence? So equivalence means those nodes, the nodes can see, okay, the actions taken by the agents. Fine. They can see the actions taken by the agents. Okay, so let's see one example. Fine. So we have seen ना कि हमने एक सबसे पहला जो प्रॉब्लम देखा था. What was that problem? So let's talk about this problem. Okay, this problem. है ना? What was the case? This is a payoff matrix wherein Alice and Bob are two players. So Alice is taking actions C and D. Bob is taking two different actions A and B, and based on that their utilities are known. If we will just make a tree out of it, okay. So in this case, what will happen? If we will make the tree out of it, तो क्या बनेगा इसके लिए? So इसके लिए हमारे पास क्या होगा? हम एक ट्री बना के देखते हैं, ठीक है? Let me tell you how to represent. Fine. So your tree always has a node. So this node over here. Okay. Now from here, who takes the action? Alice takes the action. What is that particular action? C is that particular action. Who takes the action? Alice takes the action. What is that particular action? D is that action. Now, since Alice took up two different actions, C and D, they have come to a node. Okay, they have reached a particular state or node ना. तो ट्री के केस में जो state है वो reach हुआ है उसको हम क्या बोलेंगे? A node कहेंगे. ठीक है? So these are the actions of the Alice. Fine. Now, on the basis of C, who takes the action? Bob takes the action. What is that particular action? Either A or B. Fine. Then on the basis of D, Bob takes the action. What are those actions? Either A or B. So these are the actions of the Bob. Okay. Now, if we see that payoff matrix, what we were getting? We were getting 2 1 if Alice takes C and Bob takes A. Okay, if Alice takes C and Bob takes A, so it was 2 3. Okay, if DA, in that case it was 3 4, and if it was DB, then 4 2. Okay, so I am just reversing the digits over here. Huh? It's because Alice took the action first, and then the action is taken by Bob. Okay, so I told you, na. So this is so first. What was the first? Players take sequential actions. Here, players took sequential action. First, Alice took the action. On the basis of that, Bob took A or B. D was taken by Alice. On the basis of that, Bob took the action A or B. Now, what was the second point? It is represented using trees, branches as players' actions, and leaf as payoff. You can see the actions A, B, C, D, those are the branches. And what is the payoff? They are the leaves. Okay. Now, third point, what it says about dotted ellipses. So, you see, which are those nodes that will be encircled using dotted ellipse? So, it will be these two nodes. These two nodes will be dotted ellipse. Why these two nodes will be dotted ellipse? Because I told you ना कि यहाँ से हम लोग बाकी के actions देख सकते हैं. So dotted ellipse. So what happens? Actions देख सकते हैं का मतलब क्या होता है? They are basically means if you take action C from here, the action of Bob is known कि भाई A होगा या B होगा. Okay. Now you see what happens that may be possible that a player takes more than one action in a tree, है ना? So that you are seeing that Bob may take A or B, है ना? Or it may be possible that if player can have different actions depending on which node in the tree it is in, है ना? तो अभी हम लोग क्या देख सकते हैं कि if a player can see others actions that come before him, then his action can vary. जैसे कि यहाँ पे क्या होता है, बॉब जो है इट कैन सी द इफ इट कैन सी द एक्शन ऑफ एलिस, ऑन द बेसिस ऑफ दैट इट कैन वेरी एंड से दैट ओके एलिस ने सी खेला है, ओके सो शी विल गेट लेट अस सपोज 2. So I will no if I will play the action A, then I will get utility 1. No, I will play B because I would like to have more utility than Alice. So Bob will play that B action. Fine. So over here, what is happening? So we can say that rationality is getting achieved. Okay, but on the basis of what? On the basis of the fact that Bob can see the action of the previous player. Okay, that is Alice in our case. Okay, so we can also write it in this way, or we can draw this diagram in this way. Okay, wherein Alice takes two different actions C and D. Okay, and based on that, Bob takes another action A or B. Okay, A or B, they reach certain points. Okay, here I forgot to mention those points. They have to reach certain node, na? Fine, and they are getting some values. Okay, these values are not with respect to the values of the utilities that I have given over here, है ना? So they are getting some values on reaching over here, है ना? So we can say that acha, now here I have excluded the dotted ellipses, na? So what is happening over here when we exclude the dotted ellipse? So it is known as, so in extended form games, we if we try to eliminate the dotted ellipse, so then your problem is same to the minimax algorithm. Okay, it will be equivalent to the minimax algorithm. So now in this particular case, you can say that uh, Bob, if he tries to choose B, so it will choose B on the basis of what? When Alice choose C. Okay, Alice chose C. है ना? Why? Because अगर C है तो Bob is getting so Alice is getting 5, है ना? Sorry, Alice is getting some utility more than Bob, so Bob will try to increase its utility also. Okay. Similarly, agent. So similarly, we can say that the agent, the utility of the agent from a particular strategy can be given by UI of S, where I is the agent. So its utility is S. That sorry, strategy is S. Okay, so that is, and where is this particular utility lies? It lies at the leaf of the ट्री. नाउ यहाँ कुछ कंफ्यूज होने की जरूरत नहीं है. मैंने यहाँ पे आपको समझाया क्या है कि एक्सटेंडेड फॉर्म गेम्स क्या होता है और उसको कैसे रिप्रेजेंट किया जाता है. दैट्स इट. ठीक है. तो इन एग्जामिनेशन इफ इट विल बी आस्क्ड, so it will be asked in such a way that you will be given some problem and you will be asked to solve that problem by creating a tree that is your utility sorry, that is your tree, that is your for your extended uh, uh, game tree. Okay, it is known as extended game tree, है ना? Because this is the game in extended form. फाइन. नाउ इससे आप निकाल सकते हो ना, जब आपके पास ये पता चल गया है कि भाई क्या है, तो इसके बेसिस पे आप क्या कर सकते हो, आप अपना मिन मैक्स एल्गोरिथम से इसका जो है निकालो और देखो इसका आंसर और उसका आंसर सेम आता है कि नहीं. ठीक है. तो दिस इज हाउ. नाउ a concept is there that is not very important, but I should tell you that because in the last class a lot of people asked कि भाई Nash equilibrium में we are not getting the solution that we must get, like prisoner's dilemma में if you remember 3-3 must be 3-3 has more utility than 1-1, but the defection being in less utility, but the people they try to defect, है ना? And with less utility also, but with less prison sentence they defected, है ना? But cooperate could be the better solution in terms of utility I'm talking about now. So therein when we talk about the concept of extended form of games, so here if we will try to find the solution concepts, ना, जैसे कि हमने गेम्स इन नॉर्मल फॉर्म का सॉल्यूशन कंसेप्ट्स ट्राई किया था ना फाइंड करने का, कि भाई हमारे पास 4-5 सॉल्यूशन कंसेप्ट्स थे. मैक्स मीन थे, सोशल वेलफेयर था, पेरिटो था, नैश था, है ना? अभी क्या है कि भाई हम इक्विलिब्रियम की बात करते हैं ना, वी कैन अप्लाई नैश इक्विलिब्रियम फ्रॉम नॉर्मल गेम्स. तो अगर हम सेम कंसेप्ट लगाते हैं जो नॉर्मल गेम्स में था नैश इक्विलिब्रियम का, अगर सेम को लगाएंगे तो क्या होगा कि भाई ये जो प्रॉब्लम आप देख रहे हो, ये जो 3 पॉइंट आपके जो यहाँ पे जो यूटिलिटी देख रहे हो आप 2 1 5 4 6 3 1 2, है ना? दिस यूटिलिटीज पे अगर आप लगाते हो अपने सिंपल तो आप यहाँ पे क्या देखोगे कि जो आपका नैश इक्विलिब्रियम है वो कहाँ पे अचीव हो रहा है. वो नैश इक्विलिब्रियम आपको हमेशा किस पे अचीव होगा, जब एलिस सी प्ले करेगी एंड बी जो है दैट विल बी प्लेड बाय बॉब. ठीक है. तो आप फाइंड करके देखना कि नैश इक्विलिब्रियम विल बी अचीव्ड ओवर हियर, है ना? तो बट क्या हो रहा है कि जब हम लोग इक्विलिब्रियम की बात करते हैं तो कुछ प्रॉब्लम हो सकती है. जैसे क्या प्रॉब्लम हो सकती है कि भाई जो अगर अब हम तो यहाँ बोल रहे हैं ना कि सी बी, बॉब ने बी कब प्ले किया है, व्हेन एलिस हैज प्लेड सी. ठीक है. बट मे बी पॉसिबल दैट देयर आर सम नॉइज इन द सिस्टम एंड इंस्टेड ऑफ प्लेइंग सी Alice plays D and Bob plays B. So in that case, Bob's B will not be the best response. Okay? Any noise came into the picture. Bob was knowing that Alice is supposed to play C, so I should play B. But at the time of playing, something happened and Alice played D and Bob played B. And instead of getting 5-4 as the utilities or payoffs, they get 1-2. Okay. So what is happening over here? We can say that the Nash equilibrium, your Nash equilibrium is for normal form. For normal form is susceptible to noise. That is one of the limitations of Nash equilibrium, है ना? नॉइस किसी भी फॉर्म में हो सकता है ना. So मैं ये नहीं कह रहा हूँ कि भाई यहाँ पे ऐसे मत समझो कि भाई जो बॉब है he is trying to find the he is trying to force C कि भाई हाँ Alice C खेलेगा या D खेलेगी. Okay, it's not like that. Maybe possible that Alice is communicating to Bob that I am going to play C. Choose your utility or choose your action wisely according to what I am going to play, है ना? तो पहले एलिस ने सजेस्ट कर दिया था कि आई एम गोइंग टू प्ले सी. But at the time of playing, something happened. Either it had Alice has played C, D, or maybe possible Alice played the action C. But at the time of communication, something happened. Some noise came into the picture, and C got converted to D. है ना? So what Bob received is D. So on the basis of but Bob has already played because यहाँ पे हम लोग क्या बोल रहे हैं कि भाई हम तो बीइंग अ थर्ड पर्सन वी आर सीइंग ना. बट ये हर चीज कैसे डिसाइड होगा? ये डिसाइड होगा कि ऑन द बेसिस ऑफ देयर काइंड ऑफ कम्युनिकेशन व्हाट दे आर डूइंग, है ना? तो समथिंग माइट हैव हैपेंड. सो इन दिस केस व्हाट वी कैन से दैट इट इज नॉट it is susceptible to noise, so it is not stable for noisy conditions. So in here what is needed? So for that the solution concept that came into picture is known as subgame perfect equilibrium. It is known as subgame perfect equilibrium, है ना? So what is this subgame perfect equilibrium? So what first of all let's see what is the definition. Okay, so it says that you have a strategy S star. Okay, you have a strategy S star, है ना? Now what is that strategy? So it is defined as one where all agents I and all subgames, it is true that I can't gain any more utility by playing a strategy different from S star. Okay, so what it says, if you have a strategy S star, so it means that when all the agents, your I agents are there, all the subgames the I is playing, so I can't gain any more utility by playing a strategy that is different than SI star. Okay, means I's strategy. Okay, now you must be having this na ki what is this subgame? You must be having this doubt in mind. What is this subgame? So any subtree of extended game is known as subgame. Any subtree of extended game, what it is known as subgame. Okay, so I can give you an example. Na? So here if I say that how perfect subgame perfect equilibrium can be achieved for this particular figure. So we can say that Alice is playing C. Okay, and Bob is playing B. Fine. Okay, so if Alice plays C and Bob plays A, and if Alice plays D, okay, and if Alice plays C and Bob plays B, and if Alice plays D and Bob plays A, in that case you will have more utilities, है ना? एक में 5-4 मिल रहा है, एक में 6-3 मिल रहा है. So if Alice plays C and Bob plays B, and if Alice plays D and Bob plays A, so you are getting more utilities. So over here what is going on? The subgame perfect equilibrium is getting achieved, है ना? Now you see, we must also understand when we are talking about this is very complex term. ठीक है। आप अभी अपने सिलेबस में व्हाट इज द सिलेबस दैट इज गिवन टू यू, अभी इस सिलेबस में आप ओनली बेसिक फॉर्म ऑफ गेम्स के बारे में ही आप पढ़िए, ओके। बट यू मस्ट अंडरस्टैंड, बिकॉज हम लोग अभी लर्निंग एल्गोरिथम्स की बात करेंगे ना इन कमिंग यूनिट, so there this particular concept will come into the picture, है ना। अब क्या है कि you are trying to picture or you are trying to represent your extended form games, है ना। so why you are using extended form games, है ना। so you are trying to represent your multi agent interactions, है ना। भाई यहाँ पे क्या हो रहा है कि multiple agents are getting interacted and that is very complex in nature, and that's why we have tried to use a data structure tree and we are calling it an extended form of games, है ना। so it is a basically a special case of multi-agent MDP, micro Markov decision process, ठीक है। like यहाँ पे क्या है कि it is not very simple and it becomes somewhat difficult, है ना। and the kind of solution strategies that we have seen, they may differ based on what kind of situation and what kind of behavior your agents are adopting, है ना। so you can see in your textbook also there is an example given wherein it says that now you want a multi-agent system to work, and what is the purpose of or goal of that particular multi-agent system is to play football, okay। now, when you are playing football, so who will be playing the football? So you will be having agents. Let us say that these agents are the robotic agents. Okay. So what happens? Each robot you will be assigning with specific behavior, correct? And they will have some perceptions of the world, and on the basis of their perceptions they will have some internal states also, है ना। and if definitely if a robot is going to kick the ball towards the goal, so in that way what will happen, that it will receive certain amount of utility that is higher than the other agents. And similarly you can also have some other payoffs on the basis of which on based on whether those robots are robotic agents or robots, they are trying to pass the ball among them or not, है ना। so if you consider all such kind of possible agent behaviors for all the agents in the team, है ना, and you just represent it as set of actions, so in that case what is happening, the means the players we assume that these players may achieve some Nash equilibrium, है ना। but may be possible that one of the robotic agent behaves in such a way that it tries to achieve Pareto optimal solution, है ना। so here what is happening, although the equilibrium must be achieved, but some robots are behaving in such a way that Pareto optimal solutions they are getting, and maybe possible that with that Pareto optimal solution the goal is hit, okay। so herein there is a lot of research going on in terms of the intellectual responsibility of those agents, है ना। भाई मैंने आपको बताया ना कि भाई सिंपल सी बात है, आपने एक सिस्टम बनाया है, फुटबॉल आपको खिलवाना है, लेकिन व्हाट इज गोइंग ऑन कि भाई some robots are behaving, all of them are trying to score a goal, but some of them are trying to achieve Nash equilibrium, they are passing among each other, they are doing something so that all the cooperation can be achieved. But at the same time some of the robots can also think that okay, at this particular point of time Pareto optimal solution is better than what is going on in the team, he can secure the goal, and at the same time it will be a win-win situation for that particular agent also and for the whole system, because finally that particular robot is trying to score a goal, correct, and goal is required for the team to win that particular game, है ना। so this is a very contradicting situation, and we will see कि भाई in coming time कि भाई कैसे हम learn करवा सकते हैं अपने system को, है ना, for the purpose of getting this means for the purpose of better multi agent interaction to be achieved, ठीक है। now with this we are finishing the games in normal and extended form. For further reading you can refer the chapter 3 from Vidal textbook. So this is for your further reading and understanding. Okay, and this is the second part of your unit 3 that we are currently going forward with. Okay, so this is for your further reading purpose. Okay, if you face any difficulty, we will discuss in the class, or else we will go forward with the next topic of the unit. Okay, so till then, thank you very much. Have a nice day.